Welcome to another episode of my exercise series Introduction to Physics. Today we are going to focus on Hooke's law, and we will focus in particular on the interaction of what do the forces mean with respect to energies and in particular with respect to work. So without further ado, let's get on with it. A coiled spring that you might remember from school as in spring scales has been pre-stretched by a force F1 equals 1 Newton. Now it should be stretched further by additional 10 centimeters. This requires a work of 0.6 joule. A. What initial deflection x1 did the spring have? And B. What are the spring constant and the final force? So let's put down at first again what are the given values and what are we looking for. The given values and variables: F1 equals 1 Newton, the distance s by which we further stretch our spring is 10 centimeters, and for us to not have to worry about recalculating this value into a basic unit later on, we can do it right here. 10 centimeters equals 0.1 meter. And in addition, we have given the work as 0.6 joules. And we are looking for three particular variables. First of all, in point A, we are going to calculate x1, and in point B, we are going to calculate the spring constant K and the final force F2. Let's have a look at the sketch. Here on the left hand side you can see the, initial part. So there's just the spring that is put on some surface hanging downwards. Then it is going to be pre-stretched, and we know that this takes a force F1 and correlates to a distance of x1. And actually the force F1 is given and x1 is unknown. After this has been done, we want to go and stretch it further by a distance s. And we know that this requires a certain work, W, that is given. And we are going to look for the final force F2. How do we calculate this? Well, first of all, we have to know that this whole problem is basically based on Hooke's law. Hooke's law states that for an elastically deformed material, in our case here the spring, the expansion is proportional to the applied force, which means that the force F equals spring constant K multiplied with the expansion x. So this is very basic, and it means that in our pre-stretched case, F1 equals K multiplied with x1. And as I said, x1 is the variable we are searching for and F1 is given, but we don't know what K is. Can we get it from somewhere? Yes, we have given in addition the work. And we know that work W equals the integral over f dx. And in our particular case, the boundaries start at x1 and go to x2, because this is exactly the range in which we have given our value for the work. We don't know what f is? Well, in a certain way we do. We know that f is a function of x. So basically we need to calculate the integral over k multiplied with x dx. And the solution to this is rather simple, because then the work is simply k times 1/2 x squared in the boundaries between x1 and x2, which means nothing else than that the work W equals K divided by 2 multiplied with x2 squared minus x1 squared. Does this help us? Yes, we are looking for k in this particular case to substitute it. So k equals 2 times w divided by x2 squared minus x1 squared. And we can put this simply into our equation f1 equals k times x1. And if we do this and have a closer look, we can see that yes, f1 is given, the work w is given, but we are looking for x1 and there is still an x2 which we don't know much about, or do we? Well, if we have an additional look at our sketch, we can see that yes, we do know something about x2. x2 is simply x1 plus s, the distance we are going to stretch our spring additionally. So we can take this into consideration, and what we get is an equation that looks a bit complicated, but let's make it easier. In the first step, we take x1 plus s squared and rewrite it such that we have x1 squared plus s squared plus 2 times s times x1. And then we can see already that here we do have an additional term with x1 squared but a negative sign, which means that we can simplify our equation. And if we multiply our whole equation by s squared plus 2 times s times x1, we get a rather simple equation. And we know that x1 is the only variable we don't know anything about. It's exactly the variable we are looking for. So let's take the two terms that contain the variable x1 and put them onto one side of the equation and the remaining term on the other side, and then we can simply write x1 as f1 multiplied with s squared divided by 2 times w minus f1 to s. And since we've given all values on the right hand side in their basic units, we can calculate the value for x1 that we are looking for, the initial deflection, as x1 equals 0.01 meters. And yes, this is very small, and let's recalculate it. The initial value for s was given in centimeters, so let's do it here also. x1 equals 1 centimeter. This isn't actually much, but it's also not everything we've been looking for. In addition, we are looking for the spring constant. But this is not too complicated now at this point, because we've already said that k equals 2 times the work divided by x2 squared minus x1 squared. And if we know that x2 is nothing more than the sum over x1 and s, then we can calculate it right away. And what we get is that the spring constant equals 100 Newton per meter. Are we done yet? No, we still have one thing left to do, which is actually the calculation of the final force F2. But again, this is not complicated because we know that just as F1 was k times x1, F2 is k times x2. And it's still here on the right hand side. x2 equals x1 plus s. And since we know what k is and we've already calculated x1, we can do it right away and say F2 is nothing more than 11 Newton. Now, before coming to an end, let me please add that yes, there are elastically deformable materials where the expansion and the respective forces correlate in a linear fashion. However, you can go beyond. Of course, there are materials that do not follow Hooke's law. And then again, there are materials like our springs that do have a linear correlation between the expansion and the respective force. But when the forces that you put on the spring are too strong, you can actually deform it beyond this elastic regime where when you take the force away, the spring goes back to its original form. And when you do it plastically, the deformation, then no, there is no turning back. And with this being said, I hope this exercise was helpful to you. And if it was, please consider subscribing. And I hope to see you soon for the next exercise. Bye!